Let's look at this very simple circuit analysis example. We have a circuit with a voltage power source with V as the voltage output and 3 resistors connected as shown. The resistors have resistances R1, R2, R3 respectively. Those are known parameters provided by the user, and we need to determine the 3 currents I1, I2, I3 that flow through these 3 resistors respectively. So to solve these 3 unknowns, I1, I2, I3, essentially we need to set up a system with 3 linear equations, and then we can use the computational tool to help solve those. So how do we set the problem up? Well, I'm not going to explain the circuit analysis in great details, but to solve this kind of problem, there are 3 essential things that we need to know. The very first thing is Ohm's law, which is one of the most fundamental laws in circuit analysis. Ohm's law states that for a resistor with a resistance R, if we know the current flowing through it is I, then there's going to be a voltage drop across this resistor along the direction of the flow of the current, and that voltage drop equals to I times R, which is the product of current and resistance. So you can rewrite this equation if you want to. So let's say if you know the resistance and you know what the voltage drop is across this resistor, then you can also calculate current, which equals to V over R. The remaining 2 things are Kirchhoff's 2 fundamental laws. The first one is Kirchhoff's voltage law, sometimes known as Kvl. It states that for any loop in a circuit, the algebraic sum of all changes in voltage must be 0. A loop in a circuit is essentially a closed path. So in this given circuit, we have overall 3 loops. We have this small one right here, this one right here, and lastly this bigger one. They are all closed paths in the circuit. Therefore, according to Kvl, Kirchhoff's voltage law, along each one of these loops, when you add up the change in the voltage will increase across this voltage power source, and then voltage will decrease when current flows through the resistor, as we talked about earlier. And when you add up all these increases and decreases, overall the total will be 0. Kvl is essentially a law derived from the conservation of energy because voltage is associated with energy. And lastly, we have Kirchhoff's current law, Kcl, which states that at any node in the circuit, the total input currents must equal to the total output currents. A node is defined as the connection between 2 or more branches in the circuit. Therefore, in this circuit, we have overall 6 nodes. Therefore, for every single one of them, the current coming in must equal to the currents going out. And Kcl is essentially a law derived from the conservation of mass because it deals with current, which is the flow, the opposite flow of electrons, and electrons are mass. So with these fundamental laws introduced, now let's look at how we can write our equations. Let's first start with writing Kcl equations. Remember, as I mentioned earlier, overall we have 6 nodes in this circuit. Therefore, technically we can write overall 6 Kcl equations. However, how useful are they? Do we really need to write all 6 of them? So we need to do a little bit of analysis. Think about it this way. If we write a Kcl equation of this first node here, what's going to happen is we will come to the conclusion that this current coming in to this node equals to this current going out from this node, which is kind of obvious that if the current has no bypass to branch out, the current will not change. Therefore, this is really not going to be very informative in our problem solving. But if we write the Kcl equation of this node, we have the current coming in, that is I1, and then we have the 2 currents going out, I2 and I3. Therefore, I1 must equal to I2 plus I3. In other words, I1 minus I2 minus I3 equals to 0. As you can see, this equation includes all three of our unknowns. Therefore, this is a very informative, useful equation. And this is our equation number 1. And then you will realize that you cannot write any more informative equations. For example, if you write another Kcl equation of this node right here, you will see that the new equation you write is essentially the same as equation 1 that I just wrote. Now let's move on to writing Kvl equations. As I mentioned earlier, you can write a Kvl equation for every loop in the circuit, and we have 3 loops in this circuit. Therefore, overall, technically, we can write 3 Kvl equations. However, not all of them are going to be independent, therefore not all of them are going to be useful. So let's start with this small loop right here. Remember, to write Kvl equation, we are counting the voltage change. So at first I have a voltage power source, and that gives me a voltage increase. And then along this loop, current flows through resistor R1 and then resistor R3. When current flows through these two resistors, every time the voltage drops. And that amount of voltage drop is determined by Ohm's law. Therefore, we can write the first Kvl equation plus V, that's the voltage increase from the power source, minus I1 R1, that's the voltage drop across the first resistor R1, minus I3 R3, that's the voltage drop across resistor R3. And that total algebraic sum equals to 0. So that's our overall equation number 2. And then I'm going to write the Kvl equation for this big loop right here. Again, I have a voltage increase from the power source, and then the current flows through 2 resistors, R1 and R2, and I have the 2 voltage drop determined from Ohm's law respectively, I1 R1 and I2 R2. And that's my third Kvl equation. You can try to write a Kvl equation for the third loop that we mentioned earlier, and you will realize that the third Kvl equation you can write actually can be derived from the previous 2 Kvl equations. Therefore, that would not be an independent equation. So now we have overall 3 equations, and we have 3 unknowns. Therefore, we can set up our system of linear equations to solve for all 3 of our unknowns simultaneously. Now we are ready to set up the matrices in Excel to solve this problem. Again, here are the 3 equations that I wrote earlier. The first one is a Kcl equation. The second and the third one are Kvl equations. In these 3 equations, the only unknowns are the 3 currents, I1 through R3, the voltage, R1 through R3, the resistances, they are all given information. And I put them here in this little input area. Don't forget, you want to set up your Excel file in a way that when the user or you change these values, your calculation procedure is still valid. Your Excel file is still able to generate the correct answer. Okay, so now I'm going to set up a coefficient matrix that represent the coefficients of my 3 unknowns, I1, I2, I3. So I want to make a note here so I know that these are my 3 unknowns in this order. Okay, so this space right here is my coefficient matrix. So from the first equation, the first coefficient is 1, and then -1, and then -1. From my second equation, the coefficient for I1 is -1 times R1. You want to reference this cell instead of just typing in 330, because remember, we want to be able to change the inputs and still generate the correct answer. So that's I1. I2 is missing from the second equation, therefore the coefficient is simply 0. I3 equals to -1 times R3. And then similarly from the third equation, so I have the same coefficient for I1, I2 now equals to -1 times R2, referencing this cell, and then for I3 the coefficient is 0. And over here, let me set up my constant matrix, which contains the constants from my 3 equations. Remember, you need to rewrite the constants to the right hand side of your equations. So from my first equation, the constant is 0. From my second equation, I need to rewrite this v to the right hand side. So when I move this v from left hand side to right hand side, that becomes -1 times v right here. And same thing for the third equation. Now my solution. Again, my solution is going to be a 3x1 column matrix, and I can go ahead and do this directly. This equals to the matrix multiplication of 2 matrices. The first one is the inverse matrix of the coefficient matrix, and then the second one is the constant matrix. Control Shift Enter, and this is in the unit of ampere. And then you can convert this by taking the solution matrix multiplied by a scalar 1000, Control Shift Enter, and now the unit is given in milliampere. So I can put my I1, I2, and I3 here. So that completes this problem. You can change the input or any of the resistances, and you can see that this solution area will update the answer automatically. And that's the advantage of linking to the input cells in your formulas instead of typing up the inputs directly in your formulas. So this completes the problem, and once again, we used the matrix function in Excel to solve a system of linear equations. But before that, you will need to be able to write these equations yourself based on your knowledge of circuit analysis.